Okay, so I'm going to take a second and go over this problem. This is one of the trickier ones that I always think of for the AP problems. I kind of remember every year explaining it a couple times, and it is tricky, and it takes, for some people, it takes having it explained to you several times. So that's normal. You may need to repeat the video. Um, the first part is just about the slope field, and I think you all can calculate what these slope field values are. And in the rubric, it says that they're correct approximately relative to each other, so that they're positive and negative, and like you can, even in my drawing, it's hard to see. This is supposed to be the steepest. This one's supposed to be a little flatter. This one's supposed to be a little flatter. Um, I think in the on the top row, you get something like positive 1/2, then positive 1, and then positive 1.5. Um, so that's part A. Part B says find the second derivative in terms of x and y and describe the region in the xy plane in which all solution curves to the differential equation are concave up. So I'm going to take the second derivative, and I'm going to get 1/2, because I took that with respect to x. Oh, by the way, I'm sorry to pause in the middle of what I was doing, but this is just one thing that's interesting to note about this particular differential equation, is that these two terms are being added together. It's additive, and instead of being multiplied to each other. And so it doesn't come up in this problem itself, but when the x's and the y's are being added or subtracted, you cannot separate and integrate them. As hard as you try, they could say that it's possible and you could keep trying and trying and trying, but it's impossible to do it. And so there's another method to do it with those things. And this is the case where we're not using that other method, but it's still something to notice about those differential equations, is that they're not multiplicative, they're additive. Anyways, back to where I was. So I got 1/2. Took this with respect to x. I'm going to take the next one with respect to y. So I'm going to get plus 1, but then I need to put in that dy dx. And so I know that dy dx has a value. It equals this expression right here. So then I'm going to change this to 1/2 plus 1/2 x plus y minus 1. And so I can think of this as y prime prime is equal to 1/2 x plus y minus 1/2. And we want to know where it's concave up. So we want to know where that value is greater than 0. So the way I would just write this is, let's say y is greater than or equal to 1/2 minus 1/2 x. And on the solution manual, they actually explained like with words what that would look like, but it would look like the line y is equal to 1/2 minus 1/2 x, and then it would be the area above it. So for part C, it says let f of x be a particular solution to the differential equation with the initial condition f of 0 is equal to 1. Does f have a relative minimum, a relative maximum, or neither at x equals 0? Okay, so first thing I need to check is what is the derivative of that at x is equal to 0, or at the point, what's the point 0, comma 1? And that derivative function is 1/2 x plus y minus 1, y is 1. That equals 0. That means it's a critical point. That means we have to dig deeper to figure out it could be a minimum, it could be a maximum, or it could be a faker and be neither. So this is d squared y dx squared at 0, comma 1 is equal to 1/2 times 0 plus 1 minus 1/2, which equals 1/2. So it's concave up, therefore concave up minimum. And then part D is the part that is the place where people stumble on. It's tricky. And I think it takes a while to even figure out what they're actually asking you. For what values, find the values of the constants m and b for which y is equal to mx plus b is a solution to the differential equation. Okay, so if you think of this equation right here, if it's a solution to the differential equation, then its slope is going to be the same as the differential equation. So you can think of what is the slope or what is the derivative of this? Well, that is m. And so I'm going to set m equal to 1/2 x plus y minus 1. And then I'm going to say, but I know what y is, because y is equal to mx plus b. So I'm going to get rid of that. You can tell already that we've got a whole lot of variables. We have two variables in here, the x and the y, and then we have another letter that represents a constant. So this is going to be 1/2 x plus mx plus b minus 1. And so this is going to be a solution to the differential equation if this is true for all x values. Okay, so if we play around with this a little bit, I can make this m is equal to 1/2 plus m times x plus b minus 1. And what you, this is the part I think that's confusing. It's difficult to see where it comes from, but this has to be true for every single value of x. X is a variable. I could plug in 0, 1, 2, 3, 4, 5, or even 5 million into it. And this has to be true no matter what. And that's only going to be true if this part right here reduces to 0. So that's only going to be true if m is equal to negative 1/2. So now when m is equal to negative 1/2, I get the equation negative 1/2 is equal to b minus 1. And then that means b is equal to 1/2. And so the answer for that part, find the values of the constants m and b for which that is a solution to the differential equation. M is equal to negative 1/2, b is equal to 1/2. And I think that's one of the most trickiest, and I know that's a double superlative, problems that's on the AP FRQ problems. And this one comes from an AB exam.